Recording is rolling. It is Tuesday, May 15th. We're going to continue on this adventure of quantum mechanics. You guys are working on this journal. Okay, so for context here, yesterday I had you guys staple some pages together, cut these into quadrants. I gave you guys this list of a bunch of topics, and we covered the first four yesterday. So we're laying the groundwork for quantum mechanics, going back in history a little over 100 years ago. Okay, so I'll give you guys a recap, and it's going to take us a few days here. Right, so if you go back, let's say hundreds of years ago, there was the question, what is light fundamentally? Is light fundamentally waves or particles? There were different ideas floating around. Right? Isaac Newton, interestingly enough, said light would be made out of particles, but there wasn't a good set of technology back in the 1600s to test those. Okay? Until what eventually seemed to solidify the answer was a few hundred years ago. There was this double slit experiment. So if you take say a card and you cut a couple of slits and you shine light through, you guys remember, did I bring out the Ripple tank a few weeks ago? Ripple tank? You guys remember that? Yeah, yeah, yeah. All right, right. And I had a similar thing going on, but with water, like ripples on the surface of the water. Okay? Now, one property of waves specifically that would distinguish waves from particles is this interference pattern, which is, well, exactly this that you're looking at. Okay? And since you can do this with light and get an interference pattern, it was thought to be established, okay, well, light must be specifically waves and not particles. So this was about 200 some years ago. Okay. But then there was a problem with, well, ovens. So scientists said, okay, well, we've got light as waves, and according to this classical theory, anything in wave form, you can keep increasing the frequency, and maybe you can have as much energy as you want, like packed into a waveform. Okay? So if you look at the temperature here, this could be like 5,000 Kelvin. Okay? When you increase the frequency, hence decreasing the wavelength, okay? The spectral radiance you should get from like way off the chart, like way off the page here. Okay? But it's not what they saw empirically. What they saw was actually this blue curve here matches the 5,000 Kelvin. Right, so there was some kind of information missing that couldn't quite figure this out. Right, around the same time, so 1887, Heinrich Hertz did this photoelectric, found this photoelectric effect. Right? Couldn't quite explain it at the time. He noticed that, let's say you use a solar panel, like a solar cell, and you're trying to capture solar energy and turn that to electricity. Okay? Well, below a certain threshold frequency, you would get nothing. It didn't matter if you made the light really bright, you still got nothing. Right? But interestingly, if you turned up the frequency, then you could start to get energy. In fact, beyond the threshold frequency, if you double the frequency, you would double the energy you get from it. Okay? But there was no good explanation for that. Right? Until along comes Albert Einstein in 1905. This was his miracle year, if you ever see that phrase. Einstein's miracle year. He published theory of special relativity along with a few other papers, including an explanation for this photoelectric effect. He said, hey, you know what actually would explain this? Is if light also had particle properties, right? So we're back to, oh, well, maybe actually light is particles after all. Okay? So I was thinking about these particles being like packets of energy that he calls photons, right? Actually, every one of these, see where, how you guys labeled these yesterday called discrete packets, right? And this is where the word photon comes from, photon, photons of light. Okay. Einstein say, yeah, I'm going to call these packets of energy photons. So there we go. Okay. So now light has this dual nature. Light is both waves and particles simultaneously. So that was a weird concept, right? So 1905, right, now we got this dual nature. By the slope of this line, depending on how you look at this, right, could be called a Planck's constant. So, and it goes into this equation. So E equals HF. So again, beyond the threshold frequency, if you have any frequency beyond that, and you multiply by Planck's constant, you can predict how much energy you'll get out of it. So it's this extremely tiny number. I think this is the smallest number you've seen up to this point, like 10 to the minus 34. As these squared units, joule seconds, right? Until immediately after we establish a Planck length and a Planck time, right? Which are, okay, so even smaller numbers, but of course they got different units, so kind of apples and oranges. Okay? But this is like a quantized version of the universe. Like is the universe in a way pixelated? Like, well, kind of in a sense, right? So talk to a physicist will say it doesn't really make sense to talk about distances smaller than this or time shorter than this, right? And yeah, we are talking about things that are extremely small. So we're talking about atomic size. That was actually the first one I had you guys thought here was how big is an atom? How we're talking about. And so that'll bring it up to speed. All right, so you guys go with what we got so far? That was a quick recap history so far. Right, well, since light has this dual nature, light could be a particle or wave. Along comes this French guy named De Broglie, kind of G thrown in there. It says that, I wonder if that dual nature could apply to things other than light. Right? That's where we pick up our story.
The photoelectric effect not only confirmed Planck's theory, it showed directly that bundles of energy already exist in the electromagnetic field. In other words, light comes in particles which are now called photons. But wait a minute. A century earlier, Thomas Young had proved light travels in waves. Was it now going to turn out that light is really made of particles after all? Perhaps this whole business of particles and waves was in need of an entirely fresh perspective. Louis de Broglie got a history degree en route to a career in French government, a fresh approach to physics if there ever was one. Maybe that's why, in the 1920s, he was the one to ask a crucial question. If light waves can be particles, is it possible that particles such as electrons can also be waves? To begin with, particles have energy and momentum, while waves have frequency and wavelength. Obviously, these entities have different kinds of properties. But de Broglie suspected there was some sort of connection. And Planck's theory had given a clue to what it might be. Max Planck had associated the energy of a light particle with the frequency of its wave. Going a step further, de Broglie combined this with a particle's energy according to Einstein's relativity theory. E equals mc squared. This bold mixture of wave and particle properties suggested the next step. Could particles traveling at less than the speed of light have their momentum related to their wavelength? De Broglie believed so. He thought that just as a particle's energy is related to a frequency, a particle's momentum is related to a wavelength. It was a radical idea. Not only can light waves behave like particles, but particles can behave like waves. All right, so we're going to take this dual nature of the particles and waves, and hey, can we apply this to other things too? Right? So we have the short proof here, and a lot of physics textbooks you can open up and get this wavelength of an associated particle. Right, so there's a little proof there you guys saw on the screen. Okay. So you guys remember lambda represents wavelength. Okay. H is Planck's constant. That's that 10 to the minus 34 number you guys saw. Okay. And then mv. Okay, that could be the momentum of a particle. Right, so you got that there. Now, H is so small. Remember, it's like 10 to the minus 34. It's so small that for most everyday objects, you take 10 to the minus 34 and divide by like some number of kilograms or you get extremely small wavelengths that not really being significant or making sense. Okay. But what if you had a particle that was very, very, very small and maybe had some velocity, okay? So like very particle. So what this is eventually headed towards, right? This is going to be like this next box is here, energy levels. So I'll tell you where the story's headed. Is electrons. Oh, yeah.
Can you zoom in?
I'll zoom here. So as a subatomic particle, an electron has tiny, tiny, tiny amount of mass, even compared to protons and neutrons. And that's about to be explaining electron behavior. So that.
You think of the electron as being like a wave.
Here's a nucleus here. It's like a wave. Here's an electron that doesn't make it. At that particular level, the electron's going to cancel itself if it's a wave. Maybe a little higher up. And I'm just roughing this up and hoping, well, let's suppose I went like that. See, if it can close in on itself, then that wave is permitted. And you will have an atom that has an electron that resides at that particular level. And then the next level out is one more wavelength. And one more wavelength. It's like if you made a necklace made out of paper clips. You get a certain circumference. And the next circumference you can get is increased by one more paper clip. See what I mean? Then another one. And you couldn't make a paper clip in between in terms of the radius when it's spread out into a circle if you have discrete numbers of waves. And this was a mystery for a long time. Why is it the atoms, the electrons only exist at certain levels? See? It didn't make sense with a particle view. But if you look at the electron as a wave, you can say, hey, it does make sense. It can exist at one wavelength, two wavelengths circumference, three wavelengths circumference, four wavelengths circumference, and every one of those has its own discrete radius.
Right, and that's a simplified model, but I'm actually going to use that too. Right? If you look at actual orbital shells of electrons, that they take all kind of crazy shapes in 3D. But yeah, we're going to use that simplified model. Right? Right, so did you guys learn about electron configuration in chemistry? Yeah. So see if you guys remember this way back from a year ago. Like this 1s shell can hold how many electrons? Yeah, two, right? Like one up and one down, right? Okay, so this could count for hydrogen and also helium, but that's all that can really count for, right? That blue square, hydrogen and helium, right? Right, and then when you go on to lithium, element number 3, you want the neutral atom. You can do the electron to match the third photon, right? Now it jumps up to 2s, right? And then it continues and it goes in this order. And then interestingly, it fills this 4s before it finishes off 3D and so on all the way up, right? But why those discrete levels? Now, if you imagine a model of an atom is like, okay, we got this positively charged nucleus, and we got these negatively charged electrons going around it, and you have sort of a solar system type model. Well, one of the limitations of the solar system model is like any planet could really occupy any space, right? There's no reason that there couldn't be a planet between, say, Earth and Mars. Right? Nothing wrong with that, right? But electrons don't quite work that way. Right? They can only exist at these discrete locations. Here I got another model version of this. Here we go. You may have seen something more like this. Sorry, got a corrupted file. Yikes. Okay. Well, you can kind of see it. You guys remember 1s, 2s, 2p, 3s, 3p, 3d. Got all that? Right. So same model. And then if you draw those diagonal lines, those red lines, then you can show them filling up in order. Right. So here, we're getting some books to prop this up a bit. So we got, right here's Paul Hewitt's version. Say if you need some discrete number of wavelengths to complete an orbital. Right here I have like 5 or something like that. 5 wavelengths. Okay. And then here's something straight out of the chemistry textbook. You got the 1s, 2s, 2p, 3s, 3p, 4s, and 3d, and so on. Right, you keep going on, something like that. Okay, yeah. So why is it that electrons fill specifically those orbitals in that order? They can only just exist in those discrete locations, right? Because of this wave property of electrons, which links back to de Broglie, which links back to, originally the idea came from photoelectric effect because people saw this with light first. Okay, so now we're able to explain all of chemistry. Okay? All of chemistry is based on this idea right here that you guys are writing down. Every chemical property of every atom. Okay, so just to pick one specific example of this, this is the next one. Let's say, why is glass transparent? If you look at that glass window right there in that door, right? Now you guys know visible light can go through that window. That's why you can see out to the hall. Right? You guys think back a few weeks ago. Can infrared or ultraviolet go through that glass? No. It turns out just the visible part of the spectrum. Right? But why can any light go through at all?
What makes glass transparent? Why can light get through this? Yeah, I've found a number of interesting and disturbing websites, I guess wrong answers, disturbingly wrong, in that they explain it in terms of, well, glass is like a liquid, and the molecules don't pack as tightly as they do in a solid, and therefore there are gaps in glass that the light can get through. That is wrong, badly wrong on so many different levels. Yeah, so what is going on is with glass compared to other materials, the important thing is how the atoms are arranged in the solid. And how the atoms are arranged dictates, and this is the really important bit, how the electrons are arranged. And it's how those electrons stack up in different energy levels, or the energies of those electrons, that dictates whether light can get through. Right, so what I'm going to do now is I'm going to pretend to be a photon. I'm going to move through this room, and this room represents a substance, lots of atoms, electrons dotted around everywhere. So I'm moving through with a certain amount of energy. And my job as a photon is actually to take one of these electrons from its ground state, its lowest energy state, move it up and bring it up to a higher energy level. And when I do that, basically my job is done and I'm absorbed and I don't make it through the solid. So if it's brick, for example, this is what happens. The photon comes through, it takes an electron from the ground state, moves it to a higher energy level, is absorbed, doesn't make it through. The substance is opaque. For glass and other special materials which are transparent, instead of what happens is that the difference in energy between the ground state and the high energy level, which we call the energy gap, is much too large. And as a photon, I'm coming through, and what I need to do, or to be absorbed, what I need to do is actually take one of these electrons and bring it all the way up here to this excited energy level. But I don't have enough energy to do that. I simply can't get it up there. So therefore, I'm not absorbed, and I pass through the material, getting out the other side, and so the material then appears transparent. So the energy difference between the ground state and this level, the difference between those two, we call an energy gap.
All right. So if you were to look at, well, I guess this is probably more of a molecule than a single atom. Okay. The main constituent of glass is silicon dioxide. Yeah, it's like one silicon and two oxygen. So it's like a whole molecule. But you guys can imagine sort of like this whole molecular complex. Okay. Okay. But it still has these electrons going around and these orbitals. Okay. If you look at this gap right here, this energy gap, that's what you mentioned last. Right. This energy gap is too large for photons of visible light to be absorbed. Okay, so here comes your photons. Right, it'll just have to pass through because it doesn't have enough energy to knock that electron. And so energy gap is too large for photons of visible light to be absorbed. Right. Again, that's not necessarily true for the photons in the infrared or the UV part of the spectrum, but for visible light, they'll just pass straight through. Okay. So really, I guess anything transparent. I know he's talking about glass here, but that's a similar process for, say, water, right? Or maybe like a lot of plastic bottles, right? A lot of plastic materials, same thing. Okay. Anything that's transparent. How about air? Yeah, I can see straight through the air. Ooh, that's the same process there too, right? Yeah. Not a lot of visible light is getting absorbed in any of those materials. Yeah.
Talk about quantum physics. What is quantum physics? Quantum physics is what happens to physics when we give wave properties to matter. So matter no longer is allowed to sit in just one place, like object sitting there. We've got to have it spread out like a wave. And that's why we call it given wave properties to matter. All right, so it's described by something called a wave function. All right, and so that's going to take the place of a position and momentum and all those things. Instead of that, we describe the behavior of a particle by its wave function. The wave function satisfies something called Schrodinger's equation, which kind of takes the place of conservation of energy. You can think of it that way in quantum mechanics. All right, so if we leave the particle alone, it behaves like a wave. So we're just sitting there, letting the system do whatever it wants to do, and it's described by its wave function. However, if we perform a measurement, suddenly we get something called the collapse of the wave function. So for example, if we've got a wave function that looks like that, and then we perform a measurement and we say, is the particle between these two green lines? Well, I mean, we're performing a measurement. It either is or it isn't. So it doesn't get to say, oh, part of me's there and part of, no, it doesn't get to say that. We're performing a measurement. We're asking, is it or is it not? It cannot be both. And that is going to give us a probabilistic interpretation from quantum mechanics. So the wave function will give us probabilities. It'll say, all right, if you did that measurement 100 times, 6 times you're going to find that it was between the green bars, and the other 94 times you're going to find that it wasn't. Now, really a strange duality going on there. Because if I were to leave it alone, kind of like part of it's in between and part of it isn't. But if I do the measurement, then it either is or isn't. Whole thing is or whole thing is not.
All right, so now it's starting to get weird. So yeah, okay, we still got waves and wave properties, but now it's probability of existence. So I got a particle. I'm trying to see where is that particle. Right, I measure it. You said 100 times. You measure 1,000, 1,000,000 times. Right, and if you're looking at where is this location going to be, it turns out you get this probability type graph. Right? A lot of times before I teach all this quantum stuff, I do a few days session on statistics. Is anybody taking stats or has taken stats? Is anybody taking stats? Ooh. All right. I might reverse that. I might teach you guys a little bit of stats after we finish all this quantum stuff. But there's a tie in here. In statistics, a lot of properties you see are like in bell curve shapes. So like heights of people, right? Not all people are uniformly exactly the same height. You have some people that are 5 foot exactly, or 5'5", or 5'10", or 6'5", right? Okay. But if you could make like a bell curve out of this, right? Now with locations of particles, and these could be electrons or something, you see a wave pattern that looks more kind of like this, right? Where it could very probabilistically be in the middle, and then not very likely here, but maybe more likely a little bit further away. And okay, so it kind of oscillates its probability, right? So particles exist probabilistically. So where exactly is them? See, this is different than Newtonian mechanics. Newtonian mechanics, I could give you an equation for, say, momentum and say, like, oh, there's this collision. You could know, like, exactly where is something as a function of time and run all the Newtonian equations, right? But not with quantum. Quantum matter probability where it's going to kind of show up, right? But interestingly, when you make an observation, this entire probabilistic wave function collapses, and now there is a discrete answer, but only momentarily. Okay? And then this whole probability curve resets around that observation. Okay? So say if I want to measure, is this particle between these bars here that I just hashed in, right? Well, some probability that it is. Let's say like 10% of the time it is, right? So 90% of the time it isn't, it's somewhere else, and then 10% of the time it is. But now that it is, now that it's been measured to be, right now the particle actually is there. This whole probability curve that just kind of recenter around that. Okay. I did make posters for a lot of these. I'm not showing all the posters necessarily. A lot of them are fairly similar to these notes that you guys are taking. Okay, but I can show you guys kind of a Schrodinger wave equation. This is what the map looks like. Okay, so there's a generalized version, and there's also a time-independent version. Okay, so the thing with the time-dependent version, the top one, is that as time passes, this wave function becomes more and more spread out. Okay, so at the moment you measure a particle, bam, I know exactly where it is. Okay? And then as time passes, well, now that particle could probabilistically be more likely anywhere in the universe, right? And so that's what these functions are actually looking like. Okay. All right, but how precisely can you measure exactly the location of something? And that's the question for the next one. Heisenberg.
Today, I'm doing an experiment that demonstrates Heisenberg's uncertainty principle. So here I have a green laser, and I'm firing it down towards the front of the room through a narrow slit. Now that slit can be adjusted, so it can be made narrower or wider. And the laser spot is projected onto a screen behind it. So what do you think is going to happen to this spot on the screen as I narrow the slit? Well, let's have a look. You see exactly what you'd expect. The spot gets narrower and narrower. The sides are getting cut off by the slit. Makes complete sense. And if you stop there, you would never realize that Heisenberg's uncertainty principle is at work. But if you keep going, something strange happens. As you make the slit even narrower, the spot starts to spread out. Isn't that incredible? You're making the slit narrower, and yet the spot on the wall is getting wider. The narrower you make it, the wider that spot on the wall becomes. To understand this, we have to look at Heisenberg's uncertainty principle. Heisenberg's uncertainty principle is normally written as delta x delta p is greater than or equal to h on 4 pi. So what does this mean? Well, it's about the position and the momentum of a particle. So x is the position of the particle and p is its momentum. So delta x is the uncertainty in position and delta p is the uncertainty in the momentum. Now, if you multiply those two quantities together, they must always be greater than or equal to h on 4 pi. Now, h is Planck's constant, and that deserves a video all to itself, like this one by 60 symbols. But for our purposes, it's just a very small number. So in our everyday lives, we don't come up against this uncertainty relation because everything is much, much bigger than h. But as we narrowed the slit, we were decreasing delta x for those photons. So we were getting more and more precise about where the photons were passing through that slit. And at a certain point, you come to this limit, so that if you narrow this any further, you're going to break this uncertainty relationship. So what needs to happen is the uncertainty in momentum needs to go up. I should specify this is uncertainty in momentum in the x direction, in the horizontal direction. So if before photons were going perfectly straight, now they must veer off to the left or to the right to ensure that we don't break Heisenberg's uncertainty relation. And the more you decrease your uncertainty in position, the more narrow you make that slit, the more the uncertainty in momentum has to go up. And so if these photons are going to the left and the right, that's going to produce a much wider beam. It's really, really non-intuitive, but it's the way the world works.
And so, how precisely are we allowed to know anything about the universe? No, if you go back to Newtonian mechanics, if I have some particle and it's like traveling in a straight line, I want to know like, exactly where is it, and how fast is it moving, and or at any particular moment in time. There's no problem, right? You can just run the kinematic equations, and you can know anything you want to know. But when you get down to particle size, yeah, it turns out that there is this limitation in how precisely you're allowed to know this, right? And of course, he just did that experiment to demonstrate this. So here's his single slit here. He's shining in this laser light. So here comes a photon. Okay? But as it makes this gap smaller, 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 right, that means we know more precisely its location, which means, well, there's got to be a trade-off at some point. Right? And the trade-off is we know less about its momentum, and that manifests as direction. Right? Hence, that beam on the wall would spread out. Right? So uncertainty in location multiplied by uncertainty in momentum has to be at least as big as this tiny, tiny, tiny number. You guys remember, here's Planck's constant all over again, h, like the 10 to the minus 34 number. And so divided by 4 pi, just makes it even a little bit smaller even. Okay. All right. And then for like the macroscopic world, so like everything you can see in this room with your eyes, is way, way, way bigger than that. So this is not something we ever had to worry about with any of the labs that you guys set up or anything like that. Right? But yeah, if you're measuring like photons of light or electrons or anything that tiny, yeah, you're going to run up against this fundamental limit of knowledge in the universe, this Heisenberg uncertainty.
And here we are, the granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing.
All right, so all this did so far is he's establishing what is the definition of a particle, what is the definition of a wave. Right, so you've got these two slits, fire marbles through particles, you get two bands. Okay? You fire waves through, you get an interference pattern, and you get many bands. Okay, so now we know what is a particle, what is a wave. Okay, so that's not too bad, right?
So when we throw things, that is matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. And it goes through just one and it goes through just the other.
Actually, this is not even the weird part of this experiment yet. He hasn't even talked about the weird stuff yet. Because if you have in your mind the model that, well, maybe actually electrons are really more like waves. Because I remember the whole thing about electron configurations and chemistry. Okay, well, actually, that could make sense, right? Maybe the electrons are going through really as this wave of potentials and interfering with itself. So actually, that's not even super crazy. What's super crazy was what he's about to say.
All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently. So it was aware it was being watched.
Right, this is actually consistent with something I said earlier. Do you guys remember the collapse of the Schrodinger wave equation? Okay, so electrons exist probabilistically. Well, you could really kind of extend that to all matter exists probabilistically, like spread out these probability waves with that Schrodinger equation, right? Until you observe it, and then that wave function collapses. And here we're seeing the effect of that, and it actually changes this from being like a wave property to a particle property, right? Which raises a ton of like really bizarre questions. Like, okay, well, you can even go as far as say like, does the universe even exist without an observer? Like, if there was no observer, would there be a universe? Right? That could come out of this too. Now, here they're showing the measuring device represented by this cartoon eyeball. The actual lab version of this here, I got a few on this.
All right, you ready to have your minds blown? Oh man, your minds are going to be blowing big time.
Okay. Yeah, this is a kind of a long video, so I'm just going to pause it here. You guys can see this experiment setup. But what if he shines this laser through these slits A and B, okay? And then, depending on which way the laser is routed, right, does it follow this path up top or this path down bottom? It's eventually going to reach this coincidence counter, okay? And then some of these paths, there's only one way for it to get there. Like I think this top path, like if you backtrack, well, no, hold on. No, this top one would be ambiguous, wouldn't it? Right? Because do you know if it came from slit A or slit B? That would be ambiguous, right? So it could be either, and I think you would end up seeing a wave pattern here, if I remember right. Backtrack, did it come from A or B? Well, it could be either one, right? But if it follows one of these other paths, let's see, like I'd have to think this through how this works. All right. Anyway, it's a long explanation, right? But by the time these photons reach this coincidence counter, right, whether they definitely came through one of these or whether it's ambiguous which one they came through, they'll either manifest as particles or waves, and hence you have a measuring device here. Right? Interestingly, too, is that you can make the case that this, quote unquote, measuring device is like after it's gone through slit A or B, right? So that's why the title of this video is called Delayed Choice Quantum Eraser. Right? There are like little bit variations on this experiment. So if you want the really, really even more weird version of this already weird experiment, it's called the delayed choice version, right? Where they put the measuring device like after the double slit. Okay. And so here's what I came up with, something like this. Okay. All right, so we got this double slit card. I'm trying through electrons in my case. Okay. And this top one, I have no observer, but this bottom one, I put a little cartoon eyeball here to represent some kind of observer or maybe measurement device, if you like, an observer or a measurement device. Okay. Okay, so with no measurement, no observer, okay, you get this interference pattern, okay, this ambiguity of the existence of the electron. It's spread out over this Schrodinger wave equation. Okay. But if you have some kind of measurement device, some kind of observation, okay, now that wave function collapses and it turns into a particle and lands discretely in one of these two bands. There you go, double slit experiment. All right, got one more for you guys today. You guys ready for Schrodinger's cat? Bang theory. To recap what you just said there, explanation. Okay. Say you got this closed box with this whole system going on inside it. Right? It starts with this radioactive particle and it's data superposition. Now, because radioactive particles, don't they have some half-life associated with them? Okay. Sometimes the half-life is a fraction of a second, sometimes it's thousands of years. Let's say this particular particle half-life is like 1 hour. So after 1 hour, there's a 50% chance that it's decayed and a 50% chance that it hasn't. Right? But if it does decay, let's say it triggers this whole process. It's going to trip this hammer, it's going to break this vial of poison and kill the cat inside the closed box. Right? And when I say closed box, there's no way to detect anything going inside the box from the outside. So this observer can't see inside, can't hear inside, can't feel inside. There's no detection equipment that tells this outside observer what's going on inside the box. Right? They're totally scientifically separated in the sense that you can't observe what's going on inside. Right? So after 1 hour, he's going to open the box, and there's a 50-50 chance that the particle has decayed or not. Right? And then the cat is either alive if it hasn't decayed and dead if it has. Right? But by making that measurement, from the point of view of everything we've talked about today, he's actually collapsed the Schrodinger wave equation of that probability state of that atom. Right? And before he opens the box, before he makes that measurement, that observation, everything going on inside the box really exists probabilistically. Right? Now, Schrodinger came up with this thought experiment really to try to debunk this idea because there were so many. These are all crazy ideas, right? And these ideas were emerging around the 1920s or so, 1920s, 1930s. And Schrodinger would say, well, no way could this never be true, because what if you linked the properties of the atomic world to our known macroscopic world where everything works very nice and Newtonian and follows the general relativities. Right? And so, so he's trying to debunk some of these ideas, but it actually stands around as a pretty good idea of some crazy implications of quantum. All right, so that's our pause point today.